Good evening, Pa Adit. Today we at Group 8 shall present our presentation, which is the recent advances in fuel stratified injection review. In 1973, the oil crisis meant that vehicle emission regulations were being tightened by many governments. An example being the 1970 US Clean Air Act, which became a prime focus for car manufacturers during that time period. At the time, many manufacturers tried to tune the contents and design of catalytic converters and exhaust systems as a solution to lessen their emission figures on their cars. However, this caused a major problem, which is the drop in power for most car engines. Hence, the solution is to have direct injection, which is a system where the injector injects fuel directly into the combustion chamber of the engine and in turn improve engine efficiency and vehicle emissions without sacrificing any performance. So the objective of this of direct injection is to one, improve with engine thermal efficiency, and two, to improve vehicle gas emissions.
Before jumping into direct injection or otherly named fuel stratified injection, we have a little bit of history for the fuel injection. One of the earliest form of injecting fuel into the combustion chamber was using carburetors. The carburetors was using the Venturi effect, and the carburetors was using the Venturi effect, and then we also have the mechanical injection, which uses a spring-loaded system that's open and closed by fuel pressure. And now we also have the electronic fuel injection, which was first introduced in around 1970s. It uses in most cars nowadays, and it uses a pump to deliver fuel. And with that, usually we have what it's called a port injection, which shoots fuel into the intake runner. So it's outside the combustion engine, the combustion chamber. And then we have a fuel stratified injection or direct injection, which shoots fuel inside the combustion chamber. And within this stratified fuel injection or direct injection, we have what is called a wall-guided direct injection, air-guided direct injection, and a spray-guided direct injection. The wall-guided was first introduced by Mitsubishi with their 4G93 GDI engine. It injects fuel into the combustion chamber and misfire and overly damaging the engine. And then next we have the air-guided direct injection. So it injects fuel into a stream of air from the valves. The stream of air directs it into the spark plugs. As you can see from the pictures, it was first introduced by Volkswagen in early 2000 to mid 2000 on their FSI or TFSI, which means fuel stratified injection or turbocharged fuel stratified injection. It's still commonly used by Volkswagen and their sub companies like Audi and maybe even Lamborghini up until this day. Unfortunately, it also has disadvantages due to the cyclic variations. It may be difficult to combust the fuel air mixture and may cause misfire inside the engine. The flowchart procedure, and ideally I can show you more clearly with the the
research is the role of coolant in FSI or direct injection engines. So one of the study is about the impact of coolant temperature on the combustion characteristics and emissions of certified charged direct injection spark ignition engine filled with E30. So the experiment can operate in two modes in the study: all metal mode for performance and emission testing, and optical mode for optical diagnostic, such as high-speed direct photography and particle image velocimetry. So in this particular study, the operating parameters such as engine speed, injection, intake temperature, and pressure, etc., of the two modes were kept the same. And the cross-sectional schematic of the optical engine and its combustion chamber is shown in a figure in this slide, which is comprised of intake runner, exhaust runner, cylinder head, extended piston, piston top, piston bowl window, fuel injector, and active intake valve. Okay, next. So according to their results, they stated that the varying cooling temperature has a significant effect on NOx and PM emissions, and the perturbation of this parameter affects the class SOOP-NOx trade-off. So when the coolant temperature is low, the engine emits less NOx and more carbon oxide, hydrocarbon, and particulate matters. However, as the coolant temperature gradually rises to a fully warmed up state, NOx emission continue to rise and reach a maximum level at 90 degrees Celsius, consistent with the higher in-cylinder temperatures shown in the figure. So CO, HE, or hydrocarbon and PM emissions drop with increased coolant temperature, indicating better fuel-air mixing and higher combustion efficiency. In addition, figure C on the right side of the slide shows that the exhaust gas temperature increases from less than 220 centimeters to more than 240 240 degrees Celsius, sorry, with the rise of coolant temperature. So the higher exhaust temperature would allow the after treatment system to heat up more quickly, thus ensuring a more rapid light off of an oxidation catalyst, for example. Okay, next. So this figure depicted in the slide shows the combustion efficiency under different cooling temperature. Generally, with the same fuel injection mass per cycle, combustion efficiency will influence the IMEP or indicative mean temperature directly. So comparing the indicative mean temperature between 45 degrees Celsius and 90 degrees Celsius, it could be found that the IMEP at 45 degrees Celsius drops 5.5% from that of 90 degrees Celsius, while the combustion efficiency only drops 3.1% in relative value. This suggests that inefficiencies other than combustion inefficiency also amplify for a lower cooling temperature. Normally, indicative mean effective pressure is affected by combustion efficiency, for example, like heat put, and outward heat transfer, as well as the phasing and duration of the combustion. The change in combustion efficiency is primarily impacted by the air-fuel mixture preparation, including the fuel vaporization and the mass of fuel resulting in wall wetting. The greater inflammation times for operation with low coolant lead to long combustion duration. Okay, next. So from the optical results as shown in this figure, at lower coolant temperature, the flame has a higher brightness and larger areas of white yellow sooting flames, indicating that more soot particles are generated due to larger range combustion zones.
Okay, next. So in this study, so the topic is about the FSI or direct injection running on alternative fuel and fuel blends. And the study is about the experimental investigation of the use of LPG in a gasoline vehicle with a fuel stratified injection. So basically it's a case of alternative fuel usage. So in this figure, we can see the experimental setup. The experiment of the performance and emission were carried out on Volkswagen Touran with 1.6 FSI direct injection system, which had auto gas conversion kit with AKL brand hybrid LPG system. Next. So the result from this study, the experiments performed at different vehicle speeds. So first, we'll talk about the left figure. So the wheel power values at different gear levels are given. In the third gear level, the maximum power was measured as 49 horsepower in gasoline fuel at a speed of 100 km per hour. When LPG fuel is compared with gasoline, there is a 10% reduction in power value. The next, in the fourth gear level, the maximum power was measured as 16 horsepower in petrol fuel at 120 km per hour. And then when LPG fuel is compared with gasoline, there is a 1.6% reduction in power value. And then the maximum power at the fifth gear level was measured as 73 horsepower in petrol fuel at 120 km per hour. When LPG fuel is compared with gasoline, a 23% decrease is seen in power value. And the last one, in the sixth gear level, the maximum power was measured as 69 horsepower in petrol fuel at 160 km per hour. When LPG fuel is compared with gasoline, there is a 5.7% decrease in power value. And when the power values are examined, it was determined that there is an average of 10.23% power loss in the LPG mode when compared to the gasoline mode. So the conclusion is the LPG mode has power losses. And when gasoline and LPG fuels are evaluated in terms of energy values in liter basis use, this can be first explained by the fact that LPG gives 30% less energy than gasoline. And secondly, LPG fuel occupies more space because it enters the combustion chamber in gaseous phase with the air in the engine intake manifold. This problem can be fixed by increasing the compression ratio of the engine. However, this is not possible with the atmospheric engines. The engine has to be redesigned. So the fact that the average of power values is around 10% results from the occasional spraying of gasoline in the combustion chamber together with LPG while operating in the LPG mode. The system consumes around 2 liters of gasoline as well as an average of 100 km using LPG. And then for the right graph, we can see its effect on CO2 emission. We can see that by using LPG, this CO2 emission is much lesser than when using gasoline. But the trade-off is again from the left graph is the power loss. Okay, next. So this is another study. So it's about investigation on a high stratified direct injection spark engine or DISI engine filled with methanol under a high compression ratio. And we can see here the engine setup schematic. The experiment is conducted on a modified 6-cylinder Scania D13 heavy-duty engine with only one cylinder fired and the rest in motor run. So the schematic diagram shows the engine, air intake, and exhaust manifolds, including the exhaust gas recirculation or EGR control system in the test cell. We can see. Next. So the result is this numerical model. And this numerical model is used to investigate the combustion characteristics of methanol diesel engines at different operating conditions. First, the effect of SOI or start of injection on the combustion process of methanol DC engine are studied. As seen on the figure, the combustion process of methanol DC engine is highly sensitive to the variation of the start of injection. Generally, the peak pressure gradually decreases with advanced SOI. However, a non-monotonic variation is observed for the SOI range from -33 to -37 CA after top dead center. When SOI is advanced to -41 degrees Celsius ATDC or after top dead center, the flame propagation is so slow that the peak pressure is very low, resulting in very low fuel efficiency and high instability. Thus, only the SOI from -23 to -37 degree Celsius ATDC is regarded as the operable range for this engine. We note that there is a 6 degrees Celsius difference in the operable SOI range between simulation -23 to -37 and experiment -23 to -31. This difference is attributed to the accuracy of the RANS model and the uncertainty of the initial and boundary conditions in the simulation. And then next. Lastly, we can see the variation of the combustion durations of these different cases of ST or starting time. We can see that the combustion durations become shorter, especially for the cases with earlier start of injection. And that is all for the result of this study. And then next, that is all for our presentation of Group 8. Thank you, Pak Aditya, for your attention.